Our goal for this concrete dynamic model was to create a workable representation of the atmosphere with all materials appropriately to scale. This model allows students to work with the model and to gain an appreciation for the true size and thickness of the various layers of our atmosphere. To achieve this goal, we had to find materials that were appropriately thick for the atmospheric layers in respect to the scale of a globe to the Earth's true circumference. In a cross-section, the troposphere, stratosphere, and mesosphere being represented to an accurate size in centimeters based on the conversion value used in relation from the globe to the Earth. To begin our process, we took a standard 12-inch classroom globe and found the conversion ratio between the globe's circumference and the Earth's circumference. Since we planned to create as realistic a representation of the atmosphere as possible, we had to dismantle the globe so as to cover it completely with our atmosphere. To do this, we cut the top connector off the globe. This allowed us to remove the globe from its stand without having to cut the stand itself or the globe. The globe can be easily reattached using a long screw or nail, which allows for the globe to spin normally again. Since many images and models depicting atmospheric structure are not to scale, we focused on finding the accurate width for our atmospheric layers first, and then found materials to meet these measurements. To ensure our materials were accurately sized, we calculated to scale the width of the atmosphere using the globe to Earth size ratio, and then used a digital caliper to find appropriate materials. We ended up using two materials for the atmosphere, the first being a pair of sheer stockings to act as the troposphere, and a thicker blanket material to act as the stratosphere and mesosphere. We took these materials and cut them into the appropriate shapes and sizes, ensuring that when the material was stretched, the width was to scale. We cut our materials and created drawstrings at the bottom to close the material tightly. We used an elastic band on the blanket material and a thin yarn for the stockings as the drawstrings. After these were completed, we were able to show the thickness of the troposphere, stratosphere, and mesosphere to scale with the globe. We ensured that the two layers of fabric had holes on the top and bottom to allow for the globe to be put back onto the stand. The troposphere is put onto the globe first. The properties of the stockings fit well with the representation of the troposphere, with students being able to observe the material's flexibility and porosity relating to the intake and output of radiation. This representation also gives students an idea of how fragile and thin the troposphere is, and can alter students' perceptions of how high off the ground weather occurs. Next, we put the heavier material over the tropospheric layer to represent the stratosphere and mesosphere's relative positions. The blanket material can also help students recognize how the atmosphere is an insulator. This model is part of an inquiry-based activity where students will be able to work with a collection of materials and guess how thick our atmosphere actually is by comparing familiar items to the globe. We decided that the materials we provide students with should have meaning, so we use accessible distances and materials to allow for students to connect with the scale more easily. We chose all of our materials to fit a variety of true distances. We scaled these distances to fit the globe and found common household materials that fit the measurement requirements. For these materials, we used a milk carton, wax paper, a plastic produce bag from the grocery store, a box of matches, the blanket material, 5 index cards, and a 31 by 38 cardboard shipping box. Once the materials were measured, we labeled each with their relative width for students to be able to compare to the globe. The piece of plastic bag had a width of 0.001 centimeters and represents the height of the Empire State Building. The piece of wax paper was doubled over and had a width of 0.004 centimeters and represents the height of the highest peak in New York State, Mount Marcy. The stack of 5 index cards glued together had a width of 0.095 centimeters, which represents the average thickness of continental crust. 3 layers of the blanket material sewn together had a width of 1.67 centimeters and represented the atmosphere's thickness out to space. The milk carton has a width of 9.71 centimeters and represents the distance between the west and east coast of the United States. The box of matches had a width of 12 centimeters and represents the width of the Atlantic Ocean from England to the east coast of the United States. And the shipping box had a width of 30.39 centimeters and represents the diameter of the Earth. By allowing students to work with these differently sized materials, they are able to alter their mental models and configure a new experience to observe how thick the atmosphere truly is by connecting it to concrete, measurable, and familiar distances. Along with our physical model, we also created a set of illustrations to give a detailed breakdown of the atmospheric layer structure that also allows for further student research and room to learn about the individual layers of the atmosphere. We built a model to show students the true scale of the atmosphere in comparison with the Earth. This model will allow for students to revise their mental models and avoid common misconceptions. We felt that by giving students an opportunity to manipulate materials, they have a concrete experience that will help shape their mental model for the structure of the atmosphere, which cannot be gained from a two-dimensional image alone. However, our model is not complete and hides some aspects of the true nature of the atmosphere. Our model does not show all of the layers of the atmosphere or the pauses between the layers. We decided that the scale for the layers of the atmosphere that have the biggest effect on human life were the most important to represent. We have made up for this hidden information with our drawn scale models, which are much more detailed, and by using the full width of the atmosphere in the hands-on activity. We were also not able to represent the changing density or differing composition in the atmospheric layers without compromising the needed widths. This information could be filled in when discussing the illustrations of the atmospheric layers.